Assalamu alaikum. So in this lecture, we will be covering demodulation and detection. Figure 3.1 shows two basic steps of demodulation and detection of digital signals. As you can see in the figure, the received signal is consists on transmitted waveform and noise. And we are considering AWGN noise. That means AWGN channel has been considered, or the noise has been modeled using AWGN. So the received signal, that is R of t, is equal to S of t plus N of t, where S of t is the transmitted signal and N of t is the noise added with the transmitted signal. So this received signal or waveform first goes to frequency down conversion for band pass signals, because we transmitted a modulated signal. So we down conversion means demodulation. We separate the transmitted signal from the carrier frequency. So it is for band pass signals. We have best band signal and band pass. Carrier frequency is in the band pass, and your information signal is your baseband signal. Then we have receiving filter, equalizing filter, compensation for channel induced interceivable interference. Now, it's the beauty of digital communication that we are not concerned with the shape of the waveform. We are concerned with the detection of the waveform and what is in that waveform that matters. If the waveform shows us high voltage, that means it is 1. If it is low voltage, it is 0. So if there is any uh, like discrepancies in the shape of the waveform, equalizing filter will help us the threshold comparison. That is the second step, detect step. It will rectify any discrepancies in the received waveform and will make the signal or prepare the signal so that we can understand, so that the next step can understand the meaning of waveform and extract the um, information from them. So equalizing filter are the equalizer, job of equalizer to remove any uh, unwanted signals which are like uh, destroying the shape of the waveform. So equalizing filter try to again shape out the receive signal uh, to the signal actually that was transmitted. So this receiver performs two basic functions: demodulation to recover a waveform to be sampled at t is equal to n t, and detection, that is decision making process of selecting possible digital symbol. So this t is equal to t, that is one sample is selected, and that will be goes into this detection. This threshold comparison will decide whether the received waveform voltage represents symbol 0 or 1, or bit 1 or 0. If it is BPSK modulation, if it is another MRA modulation, then a symbol that maybe consist of more than 1 bits. So that will be decided here after passing through the equalizing filter. So equalizing filter is something that removes the noise that compensate for channel induced ISI. First is frequency down conversion, performs frequency translation for band pass signals operating at some radio frequency. that is carrier frequency or frequency at which we have modulated the transmitted signal. Whereas receiving filter performs waveform recovery in preparation for the next step detection. Filtering at the transmitter and channel typically cause the receive pulse sequence to suffer from ISI and not ready for sampling and detection. The goal of receiving filter is to recover a baseband pulse with best possible SNR and free of any ISI. An equalizing filter allows the receiving filter. It is only needed for those systems where channel-induced ISI can distort the signal. So this you can see the actual transmit signal. This is the effect of noise or the receive signal before the equalizing. This is the equalizer that it tries to match the signal with the transmitted one or remove any distortion or ISI which is present with the signal. And you can see you can trail from here. This is 1 0 1 0 1 0 1 again 1 1 0 0 1 1 1 1 1 like that. So you can trail from this signal what we are receiving. So the detector, every sample it will know, it will decide whether it is 1 or 0 from these received distorted pulses. So for any binary channel that transmits signal over a symbol period, over a symbol interval 0 to t. So t is the symbol interval is given as, for any binary channel, means there are two uh, possibilities for a bit to be either binary 1 or binary 0. So we say that S1 of t is equal to binary 1 and S2 of t is for binary 0. So the a symbol can be binary 1 or binary 0. So this only happen in the BPSK where symbol time and the bit time are the same. The received signal R of t degraded by noise N of t and possibly degraded by the impulse response of the channel. So receive signal can be given by 3.1, where you can see receive signal is multiplied or convolved with the impulse response of the channel. Transmitted signal convolved with the impulse response of the channel plus noise N of t, and this can be S1 of t or S2 of t. Where N of t is assumed to be 0 mean AWG process. We already mentioned that. And for ideal distortion-less channel where HC of t is an impulse function and communication produce no degradation, R of t can be represented as SIT plus N of t and I is equal to 1 to 0 to t. So continue with this demodulation and detection, where you can see we have optional and essential block diagrams. So frequency down conversion is optional. If the received signal is already in the baseband form, so we don't need that if the input is received in the baseband signal. If it is a band pass signal or modulated signal, then you need that frequency down conversion. Then we have receiving filter, and then we have the equalizing filter. So equalizing filter is again an optional block diagram or filter. If channel induces ISI, then you must use it to remove any shape distortion that occurred during the transmission to the transmitted waveform. Then we have detect, where you can see we have threshold comparison. We have where we have two hypotheses, and Z of t is the sample trace static, because up to this point, this is R of t. But at this point, we only allow one of the samples to be goes to the detection process. So sample by sample, a sample will be decided on whether it is H1 hypothesis or whether it is H2 hypothesis. So that depend on the sample that is being transmitted from step 1 to step 2. So step 2 sample is represented as Z, and T is the sample interval. So this is Z of T. It is either greater than hypothesis H1 or less than hypothesis H2. And this is the value that we look for. That is the threshold comparison. If the received sample is greater than this, uh, what is the gamma, then the received sample is hypothesis 1. If it is less than this gamma, then received sample is H2. And the Z of t is equal to AIT plus N of t. AIT can be uh, your binary signal A1 of t or A2 of t. And it is also joined with the noise. It is again consists on a signal and a noise component. So we decide whether the sample is greater than this gamma or less than this gamma. Based on that, we will choose hypothesis H1 or H2. And then we will say, based on this hypothesis, whether the received waveform is a symbol 1 or a symbol 0. So the recovery of signal at the receiver consists of two parts. Filter reduces the effect of noise as well as transmission induced ISI. The output of the filter is sampled at t for time t. This reduces the received signal to a single variable Z of t called the test static, and the detector or decision circuit compares the test static, that is Z of t, to some threshold gamma naught, that is where H1 and H2 are two possible hypotheses. So based on the comparison of the test static against the gamma naught, which will be some voltage level, based on that, we will say that the receive waveform is H1 or H2. So the recovery of the signal at the receiver consists of two parts: waveform to sample transformation, that is blue block diagram in the previous figure, where we convert the receive waveform into the sample. As you can see, R of t is a receive waveform, but here we only allow one sample, and that we call the test static, and that will be decided in the detector whether it is matches with the hypothesis H1 or hypothesis H2. Demodulator followed by a sampler at the end of each symbol duration t. Prediction point yields a sample Z of t called test static, and that is equal to AIT plus N of t. n naught of t and I is equal 1 to 2, where AIT is the desired signal component. Second is detection of symbol. Assume that the input noise is a Gaussian random process and receiving filter is linear. Then this component that is with the N naught T, that is with the signal AIT, will have this probability distribution function. So this is the AWG noise distribution function that we have already learned in the previous lectures. That is 1 over the psi naught square root 2 pi exponent minus 1 over 2 n naught, again psi naught whole square. So this is the likelihood occurrence of P of ZS2 and P of ZS1. Z is the test static. Probability that the test static is S2 and probability that Z static is S1. So one probability is A2 for S2 and for S1 it is A1, whereas gamma naught is in between. And the received signal can be anywhere, and from that we can decide whether the received waveform is much in occurrence with the likelihood of S1 or in the likelihood of S2. So that this is basically the diagram of the P of N naught, and both signals have same distribution. So the Z of t can be decided like this. So this particular F levels L1, L2, these are the receive levels for a particular uh, test static. So based on this, we can decide whether like gamma naught is here. So so the receive level is less than less than this gamma naught, so that can be said that it is static S2, and if it is greater than gamma naught, then it is S1. So we will do some examples that will be make this more clear. So the output is another Gaussian random process. So the chances of occurrence of S1 in Z is equal to, now instead of N we can have the Z minus A1. So because we say that Z is equal to AIT plus N naught of T. If you drop T, then Z is equal to A plus A1 or A2 plus N naught. That means N is equal to Z minus A. So instead of N naught, we can put A1 minus Z or AI minus Z. So I can be 1 and 2. So this equation can be written as, if it is the probability that this static Z is S1, is this, and instead of N we can now have Z minus A1. Similarly for S2 we can have the Z minus A2, where the psi naught square is the noise variance, and the ratio of instantaneous signal power to average noise power at a time for the sample, particular sample. So we say that T at a time T is equal to T out of the sampler is AI square plus noise variance, like a psi naught square. So you can see it's AI square and psi naught square. So we take the signal as well as the noise. So this is the S over N of a sample. T for a sample time, signal to noise ratio is equal to this one, power and noise. So need to achieve maximum signal to noise ratio. One way is to improve signal to noise ratio is to increase the power and reduce the noise variance. Now this is the job that filter does. You can see. So this is the filter basically. The second part. Or in the first part, we have filter, receiving filter here. And the second part is the decision making, that is a detector. So we want to optimize or maximize the signal to noise ratio from the first step. So instead of using any filter, we must opt some filter that will optimize the signal to noise ratio. And such kind of or such a filter is the mesh filter. Its objective is to maximize the signal to noise ratio per sample. So T represents the sample time. So expressing signal AIT at filter output in terms of filter transfer function H of F, that is inverse Fourier transform of the product H of F and S of F. So if you recall your DSP, in DSP we have transfer function of a filter or the output. So the output is equal to inverse Fourier transform of the transfer function of the filter and with the input. So in this case, the input is S of T, so that becomes S of F, and this is your filter transfer function, and this is for the Fourier transform, inverse Fourier transform. So where S of F is the Fourier transform of the input signal S of T, and the output noise variance can be expressed as, so this is the variance that can be given as N naught by 2, and from minus infinity to infinity, again the transfer function of the filter. So expressing N of T as power and the noise. So this is signal power, and this is the noise that we have. So equation 3.8 from the filter, mesh filter, we something like 3.48. Now, according to Shor's inequality, when we have the integration of two functions, f1 and f2 of x square, that will be less than or equal to the two different functions. These two functions can be separated into different integrations. But this equality only holds, or this Shor's inequality only holds if the two functions are like this one. One function is equal to k and f2 of x, where k is arbitrary constant, and this star indicates complex conjugate. So f1 of x is the f2 of x is the complex conjugate of f1 of x, and uh, multiply with the k, and where k is an arbitrary constant. So associate h of f with f1 of x and s of f with f2 of x, and then we get this inequality like h of f square and s of f square in 3.50. Then substitute this in equation 3.4 to yield this equation, that is less than or equal to 2 over n naught. H of f is here in 3.50. There will be in the numerator, and in denominator we also have this h of f integrated whole square. So we cancel out this one. The only thing that remains here is 2 over n naught and s of f square integrated from minus infinity to infinity, that is 3.51. Our maximum signal to noise ratio for a sample time t is less than or equal to 2e over n naught, and energy E of the input signal S of t, because E is equal to Fourier transform of the S of t. So we can replace this S of f term with E, then becomes 2E by N naught. So the S over N T, that is the signal to noise ratio for sample time t, depends on input signal energy and power spectral density of noise, and not on the particular shape of the waveform. So that is very important when we calculate the signal to noise ratio for the filter, and that filter is mesh filter. The signal to noise ratio is in relation with the energy and the power spectral density of the noise, but there is no such component of the waveform. Because in digital communication, we don't give uh, importance to the shape of the waveform because that is irrelevant. What information that waveform represents that matters. So the signal to noise ratio is your basically based on the energy of the signal received and the power spectral density of the noise, but not on the particular shape of the waveform. Like we seen in the previous figure where we use the equalizer. Equalizer tried to fix the shape of the pulse, but after even if, passing through the equalizer, the shape of the pulse was not perfect, but it is though very much understandable that what values or what bits are being transmitted using that waveform. So that detect detection diagram or detection part or the step two can easily understand from that sample that what this sample is representing, whether it is A1 or whether it is A2. So this equality for maximum signal to noise ratio that we say is less than or equal to 2e by n and holds for optimum file transfer function h naught f such that h of f should be h naught f and it should be equal to k complex conjugate of s of f and e is equal to minus j 2 pi f of t, that is 3.54. When we do the inverse Fourier transform, the uh, transfer function in time domain comes as k s t minus t and 0 elsewhere. So the transfer function should be having k constant and it should be shifted by time t. That is your 3.56 because the Shaw's inequality says that that h of f and s not f should be the complex conjugate. This one s not f. So if you apply this and you will use the inverse Fourier transform, you will get this h of t k s t minus t. So this should be the transfer function of the channel if it is mesh filter. The impulse response of a filter. This is the impulse response of the mesh filter, not the channel. The impulse response of a filter producing maximum output signal to noise ratio is the mirror image of message signal S of t delayed by a simple time duration t. So this is S of t, but this is S of minus t. So it's a mirror image and then delayed by time duration t, that is a symbol time. And this filter design is called mesh filter, defined as a linear filter designed to provide the maximum signal to noise ratio at its output for a given transmitted symbol waveform. Then we have correlation realization of mesh filter. A filter that is meshed to the waveform S of t has an impulse response this where it is delayed version of the mirror image of the original signal waveform. So you can see signal waveform multiplied with k mirror image and then it is uh, delayed by time impulse response t. So this is a causal system. I recall that a system is causal if before an excitation is applied at time is equal to t, the response is 0 for minus infinity. The signal waveform at the output of the mesh filter is z of t will be equal to r of t into h of t, where h of t is the transfer function of the filter. So the received signal goes to the filter, multiply with its transfer function, and then we say that it's z of t. But t is not one sample, but it is a total signal, total waveform, and is equal to 0 of t, r of tau, h t minus tau, g of tau. Then we substitute h of t to yield the output because this is equal to t here is equal to t minus t. So that is t minus t, and in this case t is equal to this one. So t is the sample time minus t minus tau in the bracket. When we solve this one, this will be r of tau and s of tau. So if you if you see that if we take this one sample, then these two will be cancelled out, and we the remaining thing that we will have, that is only s of tau and r of tau from 0 to t, and z of t is equal to that one, that is 3.59. So the function of the correlator and match filter are the same. Uh, Whether we can go with the mesh filter or we can go with the correlator. Both have the same output. That is z of t will be equal to this one, r of t and s of t, and this is equal to r of tau and s of tau. So from B and A, if you compare both, they both give you z of t is equal to z dash of t. That means correlator function and mesh filter have same output. So uh, it is in the hands of the designer whether it should go with the mesh filter or go with a correlator. So after filter, we go into the detection process, where mesh filter reduces the received signal to a single variable z of t, after which the detection of symbol is carried out. So the output from the mesh filter is a waveform for a single sample. Each waveform will be decided on. So the concept of maximum likelihood detector is based on statistical decision theory. So first we say that in the demodulation, we must have uh, not must have but an optional block diagram was the uh, this band pass filter, the frequency down conversion. Then we have the filter, and then we have the equalizer, and in the detection we have the detector. So the two optional block diagrams we haven't uh, emphasized. The only part that should be there, that is the filter, and that filter should be that filter that maximize the signal to noise ratio, and we say that the match filter is one of that. So match filter is one of that filter that maximize the signal to noise ratio. So we say that instead of filter, we must choose the mesh filter. And then we say that mesh filter and a correlator have the same output. So then we have the option that instead of filter, you can go with the correlator because the output is same. Now with the detector, so a detector should be with the concept of the maximum likelihood detector that is based on the statistical decision theory. It allows us to formulate the decision rule that operates on the data and optimize the detection criterion. So if we have any other detector, then fine. But if we have a maximum likelihood detector, then we can implement some decision rule that will make the detection optimize and maximize the output. Correct output, basically maximize the correct decision output. So trace static, as we have read many times, is H1 if it is greater than gamma naught, and it is H2 if it is less than gamma naught. So this statistical decision theory is based on the probabilities. So let's learn that. So you might have learned in the PSP these probabilities. We have a prior probabilities. These probabilities are known before transmission. And the probabilities of the receive sample are P of Z S1 and P of Z S2. Conditional PDF of received signal Z, condition of the class Si. See, this is a posterior probability, which is the actual probability. And this is the a priori probability that is known before the occurrence. Take an example of a two-side coin, head and tail. So before flipping the coin, if I ask you what is the probability of occurrence of head and tail, what will be your answer? I repeat, if you flip a coin uh, having two sides, one is head and other one is tail. But I haven't tossed it. But if I ask you what is the probability of their occurrence, so what should be your answer? See, we are tossing a coin, and before tossing the coin, what should be the priority? Yes, 50%. There are two possible outputs, head or tail, so their prior probability will be 1 over 2. Uh, so before an event occur of this tossing coin is an event. So before that event, you can tell the prior probability is 1 over 2. So, but after that events has occurred, what will be the probability that their posterior probability? So a prior probability of the receive system, probability of the receive sample is this one. That received test static is S1 that we have to calculate. And P of S1 and P of S2 are the prior probability. And these are the posterior probabilities. Let's suppose we toss a coin for 10 times. In that 10 times, the occurrence of uh, head is 4 times and the occurrence of the tail is 6 times. So the probability of test static and occurrence of S1, let's suppose S1 is head, is equal to 4 divided by 10, that is 2 by 5, and 6 by 10, that is 3 by 5. Okay, so so that is the difference between a prior probability and the posterior probability. Similarly, if you have a dice, if you roll it before rolling the dice, you know that the probability of occurrence of every single digit number is 1 by 8 because there are 8 faces of a dice. Sorry, not 8, 6 faces. So there are 6 numbers from 1 to 6. Before rolling your dice, you know that the probability of occurrence of every number is 1 by 6. But when you do this for like certain time, like for 10 times or 20 times, then you will have the real probability, and then we call that a posterior probability that has occurred. So a posterior probability can be determined after examining the sample. We make a refinement of our previous knowledge. Previous knowledge हमारी क्या थी कि भाई एक जो phase है in the dice rolling will be having probability of 1/6. Or similarly in head and tail, the probability of occurrence of each side is 1/2. Or here the we have two signals, two possibilities, S1 and S2. The probability of occurrence of S1 is 1/2, same as the S2. Both have the same probabilities occurrence. So, but after examining the sample, we can improve or refine our previous knowledge, and we can say that probability of S1 and S2, probability of S2 and S1. So the probability of receiving S1 while S2 was transmitted, probability of receiving S2 while S1 is transmitted. So that is the wrong decision. That is the error. Means we have decided incorrectly because the transmitted or sorry, the received signal was S1. Sorry, received signal was S2, and we say that it is S1. Similarly, the received signal was S1 and we say that it is S2, so that we make a wrong decision. So correct decision will be like this. Transmitted is S1, received S1, transmitted S2, received as well as S2. So how to choose the threshold? So maximum likelihood radio test and maximum a posterior criterion. If test static, the probability of test static Z that it is S1 is greater than probability of S2 in Z, then we have H1. If probability of occurrence of S2 in Z is greater than probability of occurrence of S1 in Z, then we have H2 static. Problem is that posterior probabilities are not known. So how to know those posterior probabilities? We use Bayes theorem. That Bayes theorem determines that the Z static is the probability of S1 in Z is equal to probability of Z, probability of S in Z, and probability of Si and probability of Z. So from here you can calculate the from the Bayes theorem you can calculate uh, these hypotheses. So what we did, we simply substitute values of I, see this P of Z S1, this one, P of S, P of Z is greater than this, then it is H1. If this one is less than this, then it is H2. So this is P of Z S2, P of S2, and P of Z. Implies that because P of Z and P of Z will be cancelled out. Both are same on each side. So the remaining other things are different from each other. So if this part is greater than this part, then it is hypothesis H1. If it is less, then it is hypothesis H2. So that is maximum a posterior criterion, that is likelihood ratio test. Simply we rearrange the equations. This P of S1 and P of S2 will be on one side, and this conditional probabilities will be on one side. So conditional probability of P of Z S1 and P of Z S2 on one side, and P of S2 and P of S1 on one side. However, the probability of S2 and probability of S1 are same. Because there are only two possibilities, and their prior probabilities will be equal to 0.5. So we can cancel out each, we can cancel them out and we can have the 1. So now the map that is more maximum posterior criterion will be equal to this one, equation 3.6 to be that we call maximum likelihood test. A ratio of two conditional probabilities where S1 part is in the numerator and S2 part is in the denominator. So this is known as the maximum likelihood ratio test because we are selecting the hypothesis that corresponds to the signal with the maximum likelihood in terms of the base criterion. It implies that the cost of both types of error is the same. Then we have the maximum likelihood binary decision that we will do in the next class. If you have any question, you can ask.